afternoon. My name is Deyong Chen from Aerospace Information Research Institute, Chinese Academy of Science. I'm very glad to be here to present our research work about resonant pressure sensor. The title of my presentation is a resonant MEMS pressure sensor utilizing high water mode oscillation. I'd like to divide my presentation into 5 parts. First, the introduction, and then design and analysis. After that, I will give a device fabrication, experimental results, and finally conclude my presentation. Pressure sensor is one of the most important applications of MEMS technology. They are widely used in this field: aerospace, industrial control, semiconductor, etc. According to the sensor mechanism, MEMS pressure sensor are divided into 3 kinds of pressure. One is piezoresistive pressure sensor, capacitive pressure sensor, and the resonant pressure sensor. Piezoresistive pressure sensor is based on piezoresistive effect, and they feature with simple structure and low cost, and high overload resistance, but they suffer from temperature drift and low measurement accuracy. For the capacitive pressure sensor, feature with capacitive detection, based on the capacitance detection, and feature with simple structure and low power consumptions. And they have shortage such as low linearity and parasitic capacitance interference. For the resonant pressure sensor, it's a kind of sensor which utilizes the frequency, resonant frequency. So it has some advantages. For example, frequency output, and there will be a long stability and very high accuracy. But they have some disadvantages. For example, complex break application process and circuit. The core component of a resonant pressure sensor is the regulators. Regulators, we can use a beam or double-intrinsic forks and other mechanical structure. For example, with a beam, we have many vibration modes. For example, the first mode is like this, and the second mode like this one. For resonant pressure sensor, mostly use the first mode oscillation for sensing, but higher order modes they have some higher quality factor and a little higher sensitivity and wider measurement range. So higher order mode resonant pressure sensor may be a potential for better performance. Researchers have started to explore this technology for using this second mode to realize the accelerometer, and we achieved a higher sensitivity, and we use the differential drive and sense configuration. Another example is multi-mode excitation technique for a cantilever beam to enhance the dynamic response for using the second mode oscillation. In our work, we did some theoretical analysis. The frequency of resonant beam with axis stress like this with F frequency, and F1, F0 is the frequency without any axial stress. And when the stress induced by the pressure is much less than the sigma C. Sigma C means the Euler stress, critical Euler stress. This can be expressed in linear expressions like this. If you operate in the first mode, the intrinsic frequency and Euler stress like this one, and if you use the second mode, they have different factor like this, and this is the critical Euler stress. If we use this frequency shift per unit molecular pressure like this one as the sensitivity, so for the second mode, the sensitivity is 1%, 34% increase than the first mode. And if we choose 10% of this resonant as the maximum frequency shift, the range of the second mode is about twice of that of first mode. To verify the results of theoretical analysis, we designed the pressure sensor. This is the structure of our device. It consists of two parts. One is the glass cape, and the other is the CSOI device. We set two resonators. One is located in the center, and the other located in the side to give it differential output. We also designed for five electron for first and the second mode, the drive and the detection. FEA simulation is applied to analyze the characteristics of our research, our device, and from this figure, the pressure sensor sensitivity was enhanced from 157 to 206 Hertz kilopascal, and 32 improvement. This is the first mode and the second mode. To verify the improvement of performance by using second order oscillation, the designed pressure sensor was made by MEMS technology. Here is a fabrication process. First, we etch the handle layer at a different depths to define the dam from and the silicon via for the lead. And then we etch the device layer by deep IE to deform the to form the beams, and then using HF etching to release the beam. After that, we go to the glass, etch glass shallow cavity to and then spattering depth to increase the vacuum, and then analytic bonding with two layers, glass and the SOI wafer, and finally linear and dice this into a chip. This is our fabricated sensors. This is the schematic diagram or our open loop test to measure the frequency response of our device. The first is the first mode, and the correct factor is about 18,000. And the second graph is the second mode, which the correct factor is 23,000 at pressure 10 kilopascal and the temperature 20 degrees centigrade. To realize the real-time and the rapid sense of the pressure to be measured, the closed loop test, like this is our circuit of closed loop. And this is a picture of our setup. I will show you the experimental results from this. This is the first mode, and this is second mode. And this one is the frequency versus the applied pressure. And this one is the frequency versus the temperature from -20 to 60 degrees centigrade. Both have the same temperature range, but the pressure range is not is different. For the second mode, the temperature, the pressure range is from 5 to 8 kilopascal. And we got this result, the differential pressure sensitivity for the first mode. For the second mode is 316 hertz per pascal for the first, and the 30 for the second, 387 for the second mode, and we have 22 constant. And the temperature in sensitivity is also diminished to 0.7 per degree centigrade from 3.3 hertz for the first mode. Based on the data of closed loop test, calibration of the fabricated microsensor was conducted by using 5-watt bipolar limiter for temperature compensation. For example, the FC means the central beam frequency is a function of P pressure and the temperature. And the frequency of the side beam also has this effect, but is also a function of the pressure and the temperature. So by these two equations, we got pressure as this expression, two-dimensional polymer, and with the least squares fit. And we got this result. The pressure range for the first mode from 5 kilopascal to 30 kilopascal. And the maximum residual fitting errors is about 5 pascal, 0.02% per scale. And for the second mode, the pressure range extended from 30 to 80 kilopascal, and the maximum fitting error is decreased to 3.5, and the relatively accuracy is less than 0.01% per scale. Finally, I will conclude my conclusion. We utilize the second mode and improve the sensitivity and extended the pressure range. This second mode oscillation has a better accuracy for the sensor. We try to use a higher, such as the third order for the pressure sensor. We should deal with the problem with signal to noise ratio for the higher order mode. That's all for my talk. Thank you for your attention.